Okay, good day, B's and G's. This is AP Calculus. I am Mr. McColley. This is the presentation for section 6.4. Let's get right into it. Today we're going to be talking about solving first order linear differential equations and using linear differential equation to solve applied problems. And we're going to do one of each. So let's get right into it. A first order linear differential equation is an equation that can be written in the form dy over dx, or just the first derivative of y, plus some function p of x times y is equal to some function q of x, where both p and q are continuous functions of x. Just looking forward, a lot of times it's a lot easier if this is a constant. And even though it is a constant, it's still a continuous function of x. It doesn't have to be, but if it is, we get lucky. So I'll move that over. Okay, so just some quick process for solving these types of equations. We're going to write it in the standard form that we just showed up in the last one right here, where we take dy over dx plus the function times y is equal to some other function of x. And then we're going to take that value for p and we're going to integrate it in the form of some new function u of x is e to the integral of that p of x. And so the general solution is just this expression, and often it's written like this. In our book, we write it like this, where and these two are the same. You just multiply both sides by this u of x, and then it brings it over to the other side. We're going to use this in both of my examples to get us to where we want to be. All right, so let's take a look at my first one right here, and I'm going to write this a little bit better. I had it up there. I don't like it. Let's see here. So it is number 22 from page 440, and the equation is y prime plus 2 times x minus 1 times y is equal to 0. Now this one is a fairly simple problem, and you can see that it fits that form that I had on the last page of notes, where this is going to be my p of x, and this thing right here is going to be my q of x. And so what we want to do first is we want to find that this integrating factor that we had from the previous one, and that integrating factor u of x in this particular instance is going to be e integral of that p value. So we have 2x minus 1, and I do looking at my notes here, I think I have a little bit of an error. It needs to be a 2 there, parenthesis, and we'll get that together. Okay, so dx. Now this integral is pretty simple. It's just u of x is equal to e. Well, the integral of 2x to the first is 2x to the 1 plus 1 over 1 plus 1, so it's going to be x squared, and then the integral of negative 1 is just x, and then normally we put a constant in there, but remember, over here we have another integral that we're going to eventually have to do anyway. So I'm going to leave this integral off, or this constant off, and we'll just say that there's an additional constant later on. All right, so now I'm going to rewrite it in this form, filling in all of our blanks. And so, oops, that's too far. Okay, so I'm going to rewrite this as y, and then u of x is equal to the integral of q of x u of x dx. All right, so filling in my blanks. I know what my u is, so I've got y times the quantity e to the x squared minus x, and I got parenthesis. I went parenthesis crazy there, guys. Sorry. Let's write it a little nicer. Let's go y times the quantity e to the x squared minus x, and parenthesis. And then we're going to take the integral of 0 times e to the x squared minus x dx. And this thing cancels out and just becomes the integral of 0 dx, and the integral of 0 dx is just some constant. So I've got y equals, not y equals yet, I'm skipping a step if I do that. So I've got y times e to the x squared minus x equal to just some constant c. Alright, so solving for y, I get y equals, and I divide both sides by this expression here, so c over e to the x squared minus x. Now remember, if you have e, or actually we don't even need it to be any e, we just do it in general. If we have a to the negative x, that's the same as 1 over a to the positive x. Well, I can do that here, and I can make it into a single form and change this all to a negative value and say that this is c times e, and when I push it up to the top, I make this whole expression negative, so I have negative x squared plus x, and that is my final solution for y. And in this particular problem, though, it does give us an initial quantity that I need to look up because I don't want to miss it. In number 22, they say that y sub 1 is, that's not right. Do it like this. The initial condition is y of 1 is equal to 2. So if I plug in 1, I get 2 out. So if I go this up, so if I go 2 is equal to c e to the negative, let's see here, be 1 squared plus 1, and those will cancel. And and again, it's not negative 1 squared, it's 1 squared and make it negative. So I get negative 1 plus 1 is 0. That gives me c equal to e to the 0, which is equal to just c, because anything to the 0 power is just 1. So c equals 2. So here is my general solution. And my particular solution is going to be y equals 2e to the negative x squared plus x. This is my particular solution. Okay, well, we got the easy one out of the way. Let's now talk about the more challenging one. And I'm going to go right to, and I got a little ahead of myself. I didn't want to have this here. Let's put a little screen shade in and bring it down. Okay, so let's look at, now we're looking at example number 4 on page 340 or 436. And it says this: a tank contains 50 gallons of a solution comprised of 90% water and 10% alcohol. A second solution containing 50% water and 50% alcohol is added to the tank at a rate of 4 gallons per minute. The second solution is being added to the tank, or as the second solution is being added to the tank is being drained at 5 gallons per minute. Assuming that the tank is stirred consistently, how much alcohol is in the tank after 10 minutes? Now, I like this problem because it does kind of show an easy example of some sort of application for calculus. Now, just think of it this way, okay? You're in the medical field. Let's say you want to talk about drug efficacy, and you want to know how much of the drug is in someone's blood system. You know, your body metabolizes those drugs and gets them out, and you want to figure out how often should I take this drug. Do I take it every 3 hours, twice a day, once a day? Well, you do something like this to figure it out, and you do tests, and then they eventually make a model based on some sort of calculus. Now this particular one is fairly interesting in the fact that we have water, or a solution, going in at 4 gallons per minute, and solution being drained at 5 gallons per minute. So eventually this thing is going to be empty, this tank, whatever it is. So let's talk about the solution, because the question says, assuming the solution in the tank is stirred constantly, and that means that essentially, even though they're pouring it in, as soon as the new solution hits it, it's completely mixed in, and you have 100% solution. I know that that's a little bit of a wonderful world of calculus situation, but we're just going to go with it. And so they want to know how much alcohol is in the system after 10 minutes. And since they want to know how much alcohol, we are going to solve this thing, we are only going to look at what happens to alcohol. We're not going to care about the water. We're going to focus solely on the alcohol. And so by doing that, we're going to let y be the number of gallons of alcohol at the time in the tank at time t. So whenever we're looking at what y is, that is the gallons of alcohol. And that makes it nice because when we get done, if we find an equation that's y in terms of t, all we got to do is plug in 10 minutes and that'll tell us what y is. And so that's our ultimate goal here. Now, because 10% of the original 50 gallons is alcohol, there are 5 gallons of alcohol in the tank at time 0. That's going to be our initial condition, and this is what we're going to use to solve for our unknown when we do our integral. Now, because there are 4 gallons of a new solution going in and 5 gallons of the mixed solution going out, the change of the amount of solution in the tank is minus 1 gallons per minute. And so we can think of that as 50 minus t gallons after any time unit t. Okay, so therefore, the tank loses 5 over 50 minus t times y gallons of alcohol per minute. Now, the reason I need this y in here is because we are adding an amount of alcohol in. So what this thing calculates is it says what portion of it is alcohol going out, because we have more going in. We don't have just the original 5 gallons. Every minute we're putting 2 more in. So some of that alcohol is going out as we move forward. All right, now because a 50-50 solution of water and alcohol is being added at 4 gallons per minute, 2 gallons of alcohol are being added per minute, and that's important. So the change in y, dy, in gallons per a change in time, dt, that's what we're looking for, we can say that dy over dt, the change in the amount of alcohol in the solution, is the let's do it this way, is the amount going in minus the amount going out. And in this particular instance, the amount going in is just 2 gallons, 2 gallons per minute. And the amount going out is the 5 over 50 minus, and it's t times ry. So dy over dt, this is a first order linear differential equation. All right. So we want to get it in that form. So we're going to say dy over dt plus 50, or 5 over 50 minus t times the quantity y is equal to 2. So our p function is going to be this 5 over 50 minus t, and our q function is just going to be 2. Now that's good. And you'll see here, because anytime we have a constant for that value, then it's going to make our life a lot easier. Okay, so let's get this thing set up. So again, we want to go back to the model that we had here, and we're going to use this. So we got to figure out what our integrating factor is. And so for me to do that, what I'm going to do is I need to integrate this thing. So I'm just on a separate sheet of paper. I'm going to separate sheet, page, whatever. I'm going to integrate this. And this integral is not too hard. I let the bottom equal 50 minus t, and so du is equal to negative 1 dt, the derivative of this. So we've got one of those. The integral of 1 over u du is equal to the ln of u plus some constant c. Now we're not going to use the c in this particular instance because, again, we got another integral to do later, and we'll do that constant when we get there. So this thing here, I'm going to bring my 5 out, integral of 1 over 50 minus t dt, and remember I need a negative 1, so if I put a negative there, I got to put a negative out there, and then I get negative 5 ln absolute value of 50 minus t And again, we would normally say plus some constant c, but we're going to do an integral later, and we'll throw that constant in there eventually. And we can get rid of these parentheses because remember, what is time? Time is the number of minutes that has elapsed since we started adding and draining water. And so it only makes sense that in the context of this problem, t has to be between 0 and 50, because after 0 minutes, at 0 minutes, you're going to have your 50 gallons, and then since it's draining at 1 gallon per minute, after 50 minutes, it's going to be empty. So t is always going to be positive, so I don't need those absolute values. And I can say that this integral here is now the ln of 50 minus t to the negative 5 power. And that works for me. So we go back to this original, and remember, we want to say that u is equal to e to the integral of this 5 over 50 minus t dt, and we calculated that, so we get e to the ln of the quantity 50 minus t to the negative fifth, and e to the ln cancels, so this is just, and I'm going to do 2 steps here. I got a negative exponent, it's going to make it positive. Those 2 cancel, so I'm going to end up with 1 over 50 minus t to the positive 5. So that's our integrating factor. There's our u, and this should be u of x. And so when I go to rewrite it, remember it's y times u of x is equal to the integral of q of x, u of x, dx. So filling this stuff in, I've got y times, and it's 1 over 50 minus t to the fifth is equal to the integral of 2 times 1 over 50 minus t to the fifth, and we're going to go dt this case because that's the variable that we're integrating with respect to. Okay, so doing this integral. Now this is not similar to what we had there. We have an expression, so we could rewrite this thing as the integral of 1 over u to the fifth du, like that, and then we can just say that this thing is u to the 5 plus 1 over 5 plus 1. Actually, it'll be, we can, let's, you know what, let me not get ahead of myself. Let's rewrite this as the integral of u to the negative fifth du, and then it'll be u to the negative 5 plus 1 over negative 5 plus 1. And that's what we're going to do with this thing. So I've got my y over, I'm just multiplying, so 50 minus t to the fifth is equal to 2 integral negative, or I got 50 minus t to the negative fifth dt. Now, because this is going to be my u, the derivative of u is negative 1. I need a negative there and a negative there. And so when I do this, I get, again, y over 50 minus t to the fifth is equal to negative 2, and then this thing becomes 50 minus t to the negative fourth over negative 4, and plus some constant c because I'm doing the integral. Now this is the constant that that takes into consideration the constant that I left out earlier. Okay, so if let's simplify here, this becomes 2 on the bottom, and I get a negative 4. So you know what? Let's just write it one more time so that we're not skipping steps. I've got y over 50 minus t all to the fifth, and this one is incorrect because I put my parenthesis before I put my t. So let's make sure we keep that straight the whole way. And then this is going to be 1 over 50 minus t all to the fourth now, plus some constant c. It's going to multiply both sides by 50 minus t to the fifth. And the reason that I'm going to do that is because I want to get y by itself. And again, going back, that was the original goal of this thing. Remember, we're trying to find y, the number of gallons in the tank after time t. Okay, so let's do that. So I get y equals, when I multiply 50 minus t to the fifth times 1 over 50 minus t to the fourth. And did I lose? No, I didn't lose anything. I'm good. I thought I lost a constant somewhere here, but we canceled it out there. And I did. That should be a 2. Sorry, because negative over a negative is a positive. 2 divided by 4 is a half, so I need that 2 on the bottom there. So that's good that I caught that. I'm sure somebody caught it out there. Anyway, back to this. Multiply both sides by this. 4 of them cancel out, so I'm left with 50 minus t to the first all over 2 plus c times 50 minus t to the fifth, because that's when I distribute to both terms, we get that. So now all that I really need to know is, what is c? Well, I have an initial condition. Remember, at a time of 0, y equaled 5 gallons. Because there was 5 gallons of alcohol in that solution at a time of 0. So if I plug in 5 here and go 50 minus t minus, you know what, let's plug in 50 minus 0 over 2 plus some constant c times 50 to the fifth, and I solve this for c, I end up, I got 5, and then it's minus, let's see here, 50 over 2 is 25 equals c times 50 to the fifth, and I'm not going to multiply that out. So I get negative 5, or negative 20. That's not even good. Negative 20 equals c times 50 to the fifth, and so c equals negative 20 over 50 to the fifth. And so my particular solution is going to be y equals 50 minus t all over 2 plus, let's see here, don't want to lose it, c times 50 minus t to the 50th. That looks good. Oh, sorry. I was just checking my work. This should be my particular solution should use c there. So I've got negative 20 over 50 to the fifth. All right, so there's my particular solution. I rewrote the general solution. I didn't want to do that. All right, so now what does this thing do? This calculates y, the gallons of alcohol after t minutes. And so if I go back up, and I know this has been a long time coming, I'm already really long. The question asks, assuming the solution is stirred consistently, how much alcohol is in the tank after 10 minutes? Well, after all that work, all we have to do is go y equals 50 minus 10 all over 2 plus negative 20 over 50 to the fifth. And this should be a 5 as well. I know some of you were writing me notes already. And this should be a 10, because we're talking 10 minutes. And that is to the fifth power. And so when I calculate all that, you can use a calculator, do it on your own, but I'm running out of time. So I'm just going to write down what I calculated in my notes. 13.446 gallons of alcohol. All right, folks, that's quite a bit. That's long. A lot of stuff there. And I know that that last problem was a lot. It's pretty difficult. But this is the end. And there is one that is similar to that on the practice work. And there is a general equation that they want you to prove in 31. I'm not going to make you do that, but I would use number 31 to plug in the information into 33, and so you don't have to come up with a lot of the things that I came up with here, because we had to actually calculate our first order differential equation. If you use 31 as your general model, all you're doing is plugging in, and you can go right to this. And I know that doesn't get rid of a lot of the work, but that makes it a lot easier to plug in. All right, that's it. 25 minutes is plenty. Have a good day. Goodbye.